Okay, so when we find the pH, we do the following. We log the hydrogen and then we change its sign. Okay, we log the hydrogen, then we change its sign. So to undo this, we have to go in the opposite direction. Yes? We have to change the sign, and then we have to anti-log it, which is basically unlogging it. Okay? So hydrogen ion concentration is technically, jumping all over the place. Okay. Well, this is very upsetting. I'm sorry. I'm just going to close this and open it again because it's having a little hissy fit. Okay. Not that I'm not having a hissy fit on top of that, but you know. Okay. Let's see if we can make this work now. Well, that seems more promising. So in order to find hydrogen given pH, we can take the antilog of the negative of pH. Yes? However, most people I know like to write the formula like this because this is one where you have a button on your calculator. You have a 10 to the x button on your calculator, yes? It's very often the inverse of the log, okay? So it's like the shift log button. If you cannot find it on your calculator, let me know. I can help you find that. Anyone having difficulty finding their anti-log button? No, okay. Now, if you have something really straightforward like a pH of 4, you don't even need to use your calculator. It's only when decimals are involved that you need your calculator. For a pH of 4, it's really super easy. You just raise 10 to the power of -4. And so that then becomes 1 times 10 to the -4. And this is where this little bit gets tricky, is that, do you see this 0 here? How many sig figs in that pH? How many sig figs? One sig fig in that pH. Because sig figs only occur after the decimal in pH. Because remember, this 4 here is not a sig fig. Why is it not a sig fig? Because it's really that 4. Yes? That 4 right there is this 4 right here. Yeah? And that's why it's not significant, because it is the exponent. What a log does is it takes the exponent and it sticks it in front of the decimal. Okay, that's what a log does. It takes your exponent, your power of 10, and it sticks it in front of the decimal. So whatever is in front of the decimal is your power of 10. So it does not count towards sig figs. Whatever is after the decimal is all the other stuff, so they are significant. So if we have 1 sig fig here, we need to have 1 sig fig here. Okay? Recall, in pH, only digits after the decimal are significant. Therefore, our answer must have 1 sig fig. Let's try another one. See if I can make this big enough for you to read. If pH is -1, now remember, is that very acidic or is that very basic? pH of -1. Very, very acidic. Okay, you've got a strong acid and it's probably also very concentrated. So if we take our hydrogen, if we want to find hydrogen, we take 10 and we raise it to the power of the opposite of pH, the negative of the pH. So if pH is already -1, we have to make it the negative of -1, which is 10 to the 1. Yes? So that's then going to become 1 times 10 to the 1 molar is how we'll write it. And how many sig figs do we need? We need to have 2 sig figs. So how are we going to do that in our number? 1.0. Okay. Let's see if we can do this next one. See if you can plug this onto your calculator and get the correct answer. Let's just make sure all our calculators are doing what we want them to. Okay. So 7.23. I get 5.8884 times 10 to the minus 8. Is that what you get? No, maybe I punched it in wrong. Let me see. 7.32 antilog. Hang on. 7.32 negative antilog. How about 4.786? Does that sound better? Okay, I punched the button wrong. 4.7863 times 10 to the negative 8. So if I have that, is my answer correct? I know I have the number right now. Sig figs. How many sig figs do we need? We need to have 3 sig figs. And so that's going to be 4 point what? 4.79 times 10 to the negative 8. And what is our unit there? Molar. Okay, so always go back to the beginning of your question and say, what am I actually looking for, right? Because sometimes those molars sneak up on us. All right, so that's basically it. So here is the chart with all the information on it. I never used a chart like this. I just knew my conversions and I knew what, I mean, obviously if I had hydrogen and I wanted to find hydroxide, I knew that KW connected those two. However, this can be a really useful little device if you just want to put everything in one place in your brain. So if you like this, write it out 3 times a day between now and Friday so that it's right there in your head when you need it. Yes? Okay. That's it for that one. Let us take a look then at 4.2D, which you just picked up today. If you have not yet gotten one, they are right here. Okay, 4.2D. Oh, I forgot to mention one thing. Silly me. Silly me. What if you wanted to get from hydronium, let's say I gave you hydronium and you wanted to find POH. There's no diagonal path, yes? You can either go down, you can turn hydrogen into pH by taking the negative log, and then you can use pH plus POH equals 14 to give you the POH. So you would take the P14 minus the pH would give you that. You could also go the other way. Yes? So you could go from hydronium to hydroxide and then down to POH. So just whatever your choice is, it doesn't matter which one you do. They're both perfectly good. Okay, and you could do that for any of the 2 corners. The effect of KW on the pH of pure water. 3 pieces of information. This is important. Put a star beside it. Maybe another star. A solution is neutral if hydrogen is equal to hydroxide. Does that make sense? If you have the same amount, then it is neutral. If you have more hydrogen, it is acidic. If you have more hydroxide, it is basic. And really, that's all it comes down to. And I know it seems super simple, but you'll see later on in this worksheet why that gets a little bit like, okay. So first of all, we're going to tackle the idea of why pure water has a pH of 7. And actually, that question is slightly misleading because pure water only has a pH of 7 at 25 degrees Celsius. At other temperatures, it does not. And that's because at 25 degrees Celsius, Kw is 1.0 times 10 to the negative 14. What do you know about temperature and K values? Temperature changes K values. Is there anything else that changes a K value? No. Okay, so just temperature. So if we're at 25 degrees Celsius, everything's good. So let's say we are looking at pure water and it is at 25 degrees Celsius. If we want to find the hydrogen ion concentration, or we could say the hydronium ion concentration, they're the same thing, then we're going to convert it to pH. Well, we know that Kw is hydrogen times hydroxide, and we know that's 1 times 10 to the negative 14. Yes? In pure water, because it's neutral, yes, hydrogen concentration has to equal hydroxide concentration, right? Because it is a 1-to-1 relationship. And it doesn't matter whether we write it the shorthand version or whether we write it the realistic version. It's still a 1-to-1 relationship between hydrogen and hydroxide or hydronium and hydroxide. By the way, what do we call this process that water is undergoing here? This is called the autoionization of water. So is this. This is also the autoionization of water. Now, because they are 1-to-1, does it make sense that hydroxide and hydrogen are equal to each other? Yeah? So they're equal to each other. So in other words, we can actually take our hydroxide term, yes, and we can substitute it with hydrogen. We can replace it. And what we'll end up with then is instead of H times OH, we'll just have H squared. Yes? So far, so good? Okay. And then if we solve for H, we take the square root of the whole thing. And we get 1 times 10 to the negative 7. That's the hydrogen ion concentration. Now, in pure water, hydrogen and hydroxide are equal, so hydroxide is also equal to 1 times 10 to the negative 7 molar. What if we plug those into our pH calculations? Well, we get pH, negative log of hydrogen, negative log of 1 times 10 to the negative 7. We get a value of 7. Oh, guess what? For POH, P means take the negative log How could you remember that? Well, I'm thinking of camping, but maybe you don't want to go. Anyway, no one knows what I'm talking about. That's good. That's good. Okay. What? You're confused? Camping? Well, if you're a lady and you're out camping, it might be more important for you to have a log there when you pee so you can like sit on something and hang over so you don't fall over. Yes? For guys, this might not be such a thing. No. So that might help ladies remember, but only ladies who go camping. So I'm not sure that this is a good analogy at all for like a little mnemonic device at all to help you remember, except for that it's so awkward that you might just remember it anyway. Yes? You might be like, wow, Miss Spence just really overshared there with her camping experience. I don't even want to think about that, except for now I can remember that it was a negative experience. So we took the P as the negative log. See? Now you'll never forget. P is the negative log. Okay. So we do the same thing and we get pH 7, and that's where that number 7 comes from. Yes? However, let's look and see what happens to Kw at some other temperatures. Okay, we're going to skim on down to the questions. Is the autoionization of water endo or exothermic, and how do we know? What would you look at to determine that? You're going to look at the temperature, okay? What is temperature doing? Temperature is increasing. What else should we be looking at? We should be looking at what's happening to the Kw. What's happening to Kw? It's also increasing. So, first thing we can say is that as temperature increases, Kw increases. And we know that Kw is equal to, what is it equal to? What's the expression? H3O plus times OH minus. And if we write our equilibrium for that, what do we put on the left of the equilibrium for the autoionization of water? We put H2O. And what goes on the right-hand side? Yeah, so if we're going to do the H3O version, we're going to put H2O plus H2O. In equilibrium with H3O plus OH minus. And so if Kw is increasing, that means the system has shifted to the which way? Right. So where's the heat term? Because as temperature increased, Kw increased. And if Kw is increasing, the system is shifted right. What side is the heat term on? Therefore, the heat term is on the left and the reaction is endothermic. I don't have room to write thermic, so I'm just going to write endo. Could you write a formula for how to calculate the hydronium ion concentration in pure water? So we're going to run a little short on time here. I'm going to ask that you guys watch the video because I'm further ahead with my block 3 and 4 classes. Okay, so you're going to check out, I'll put like a little note for you guys as to where to go on. But we're going to keep going for a moment here because we do have a moment. Write a formula for how to calculate H3O plus in pure water. Oh, look what we just did back here. We just calculated the H plus in pure water. So we had H squared is equal to KW, yes? Because we said H is equal to OH, so H squared is equal to KW, so H squared is equal to KW. So how would you calculate concentration of H? You would take the square root of KW? Yeah? Yeah. Yeah. Okay. I didn't write that very well. What? We're going to go for another minute. What is true about hydrogen and hydroxide in pure water? They are equal. And from there, you can now fill in the rest of the table, which is why I wanted to finish that one. So your homework. Now at level 2 dance studio and snowboard competitive team meeting in the dance room for 102 right now. Thank you. Okay, so you're going to do 4.2a, 4.2b, the questions, and then you're going to do this. There's a little extra stuff that I'm going to teach you on Thursday. If you want a preview of that, watch the video because it'll come sooner. So if you're like, I don't want to just learn it on Thursday right before my quiz, feel free to watch the video and learn it sooner. Okay? You're welcome.